accepted.
Once we know what we need to change, the modification itself may be, well, trivial. But the road to that enlightenment is often painful. Anyone has a clue where I got this quote from? Any idea? Spoiler alert, it's not Yoda. It's a quote from Adam Thornhill. Maybe some of you already have heard the name, or maybe you even read some book from him. So Adam Thornhill is a computer scientist and even a psychologist, and he's combining basically both degrees to try to understand what effort does it take to understand code bases. How is complexity in code bases basically defined, and what can we do about it to have a better understanding of code bases? So, in the spirit of Adam Thornhill, I welcome you to my talk, Understanding Complex Code Bases in hopefully less painful ways. My name is Grzegorz Lato. I'm one of the team leads at Check24. It's a company in Germany, about 19 locations, and we're doing a comparison portal where you can compare any kind of products and insurances and stuff. So we're a very developer-centric company, doing front-end development, back-end development, native iOS and Android development. Quite exciting. If you want to know get to know more about the company, please come to me after the talk, scan the QR code, you can even apply. Let's get in touch. This talk will be a follow-up talk that I gave at AppDevCon last year in Amsterdam. The one at Amsterdam had more theory in it. This talk will have more practice and kind of more demonstrations. Understanding complex code bases. The emphasis here is clearly on the word understanding. What does that mean? Understanding is a kind of process, and it usually takes up a lot of effort. So you have to invest effort, mostly cognitive effort, to work yourself into a code base, to maybe use a kind of tool. It requires a lot, sometimes even it's very painful. You have to think about abstractions and such things. So the question here is how to approach unknown code. And unknown code can be maybe even code from you that you have written yourself maybe 2 or 3 years ago. Or you take up maybe some kind of project, you start a new project, and I'm pretty sure everyone has been in this situation, maybe multiple times even, and I'm pretty sure sometimes it was painful. So what would be a usual approach to work yourself into this code base? I mean, you can use your IDE, you can use logging, you could ask around, you could then, of course, do multiple rounds in technical PRs, have a lot of PR cycles. You could stare at the code for a long, long time until this code stares back at you, but still, sometimes it's just even frustrating. It's very painful. It takes up a lot of cognitive effort to, like I've told you, to deep dive into the code, to understand the concepts behind the paradigms that are used, to understand the patterns, and. So this can really be painful. I mean, the thing is, it's not a negative thing because we as developers, we're doing it on a daily basis. It's part of our daily job to do this. We started this conference with the key term curiosity, if you remember from the first day. That is maybe a very good statement. Stay curious. Don't always work in the same scheme that you have been working before. Maybe think about another scheme. Maybe think about alternative approaches. Maybe those approaches can even be unusual. Maybe you even didn't think about them before. So that is the thing I would like to show you. In this presentation, I would like to demonstrate you, to show you one approach that is quite unusual, but at least it helps in different situations maybe to make 1 or 2 steps back and to look at a problem from another perspective. Network theory is the heart of complexity science, James Lewis told us in this conference. You are artists, Sander Mack. Great, let's behave like artists. Diagrams are maps that help software developers navigate a large and/or complex code bases. Simon Brown, inventor of the C4 model. Also very, very good statement. So what we're trying to do, we try to combine all of them, all of the statements, and let's see how it turns out. Before we do that, I have to tell you a small story. So once upon a time, yes, and now it's starting like Yoda. Once upon a time, I was involved in a software project, and there were at least 2 teams developing on 2 different code bases. Those were 2 apps. They were quite complex, so they had like a couple of years development time already. And then at one point in time, some people from upper management decided, now guys, you know what? It's time to merge those 2 apps. This will be such a wonderful thing. It's such a great idea. You could probably think of what the developers thought about that. Having several different architectural patterns because the teams weren't even working together, so they didn't even know each other. That was quite a challenge, a technical challenge, you can say. But the thing is, if you argue with, every developer understood, oh God, this is going to be a real pain in the ass, right? But the non-technical people didn't solve the problem. So it's hard to argue on a technical basis if you have stakeholders that don't understand the kind of arguments and the kind of things that lie ahead of you. So obviously, there were some arguments against the doubts from all developers. How hard can it be? Just merge the damn code, should be no problem. It's just 2 little apps, come on. Basically, I had to revise my strategy. Didn't work out. The argumentation was quite hard. I had to think of another approach. I had to think of something that would enable me to get in the kind of communication with all stakeholders so that they could also see the problem the same way that we as developers already analyzed it. So I created this. What you see is from 2 code bases, 2 dependency graphs. Every dot or node on those graphs represents a class or entity, could be a class, could be a structure, and the edges represent import dependencies. So class A is importing class B. Everything is coupled together. You can see on the one side there's even harder, stronger coupling, but clearly what everyone just saw in this second, I showed them this picture, boy, the plan will not work out as expected. And it took them really no cognitive effort at all. Everyone realized this in a couple of seconds. So this is the thing about choosing the right visualization to have everyone on board to be able to communicate and discuss about a problem and maybe about further planning. But before we start going deeper, let's just talk about graph theory first. We need some concepts. And don't worry, I try to minimize it as much as possible, so I will try not to bore you to death with graph theory. Let's try the shortest summary of graph theory ever defined. In graph theory, basically you have nodes and edges. Nodes can have properties, they can have numerical properties, they can have colors, they can have labels and stuff like that. 2 nodes can be connected by an edge. So you have 2 edges, they can be connected, either they are connected by an edge or they aren't. That's all. An edge may represent a relationship between 2 nodes. That means, you all know the concept because you have been using it. Think about social networks. They work exactly this way. Kind of very easy relationship. Someone here maybe is a friend from someone there. That's a relationship already. And this allows us to model dependency graphs. A dependency relationship is a kind of one-directional relationship. So basically you have arrows on the edges. So that means this thing is dependent on another thing. That's all about graph theory. Let's just make one step towards software engineering then. Nodes can be files or entities, e.g. classes, structs, methods, composables maybe. Even think of modern language paradigms from Kotlin. You can model it in any way you want. Edges represent import dependencies. That's kind of easy. Nearly every language has import dependencies. You're importing code from another entity, from another module, and stuff like that. So it works out. And now 2 essential ideas for this unusual approach. I'd like to discuss with you or explain to you those 2 ideas. So the one idea is the coloring, and the other idea is the shape of the graph. Because on the picture you saw there were some colors, maybe some kind of idea was behind this, and there was a certain shape, a certain structure. Let's start with the color. As you can see, you can color those nodes. It's a pretty good thing. When you just look at it from a kind of visualization, coloring is good because it reduces your cognitive effort to realize nodes that have a similar color probably have something similar too. They belong to each other somehow. You can even call it a cluster. So let's color our nodes by clustering. Pretty sure you know clustering algorithms or clustering approaches from statistics. Let's forget about this. Statistics is a very, very numerical thing. We will not cluster our nodes in a kind of numeric way. We will choose an alternative approach here. We will use something that is called Louvain modularity. That means it's an optimization algorithm that basically is even very fast. I think it's even n times log of n, so from a computational point of view, it's very good, very good. And it does cluster not on a numerical basis, it clusters on connectivity properties. So just think we're clustering on connectivity, which makes totally sense when we speak about graphs, because we can use the edges. So let's assume we got the coloring straight. It will work. Then there's another thing. This is called the shape, the structure of the graph. So let's create the graph layout based on some kind of physical conditions. 2 simple rules. Connected nodes attract each other. If they are connected by an edge, they pull together. There is a force, a computed force. And unconnected nodes, they repel each other. Sounds simple, but basically it is okay. Of course, there are very clever algorithms behind this, and again, we can have runtime complexity of n times log n, so this is also very fast. It's called a force-directed layout. Maybe some of you already have heard of it, or maybe are working with such things. Will help us. As you can see, you can drag those nodes away even, but they're going back to their original state, so that is a cool thing. Some of you maybe know, there is even a Foo Fighters album which is called The Color and the Shape. Very good thing. So in theory and practice are the same. In practice, they are not, unfortunately. Let's see what we can do about this. Let's see if everything I told you is true, or maybe, I don't know, let's find out together. We will start with a Java project here. I mean, it's a Java conference, it's a good start. I brought you a small demonstration of a tool that I've written, which is kind of serves the purpose here. So what you see is a generated file dependency graph of a Java code base, which have quite some complexity. There was nothing manually done, so everything was computed automatically. And you already can see there is a kind of modularity-based clustering and modularity-based structure. So the algorithms themselves found a kind of good modularity already in the source code, in the code base, and the coloring was also done independently, but both approaches found the same way. It's a kind of good way to see if you have like maybe a modular code base or if everything is like tightly coupled together. This is a positive thing. You can zoom in, you can zoom out, drag those things, play with it, do interactive actions with those things. Kind of okay. So this gives you already an overview about how files are dependent to other files. We can even do more. I mean, I told you, we can even use entities. Entities in the sense of classes or structs. I mean, let's try out. So this is the same code, only modeled from the classes and structs. Strange, it does look the same somehow. I've been lying to you. No, basically this is the case because in this code base, every Java file contained nearly exactly one class. So, of course, the structure, the coloring, the clusters, they look nearly the same. We can further enhance understandability by enabling node labels, by looking more into details, by hovering over nodes. maybe even looking up some numerical metric values and things like that. So this serves the purpose on details on demand, but only on demand. And yes, it does clutter when you zoom out and still the node labels are there. So basically we have the dependency graph. That is pretty cool. We can get a very, very quick overview of the whole code base in very, very less cognitive effort. And we can apply software metrics on that. Applying metrics is an easy thing. Like classical metrics, you would say number of methods, source lines of code, fan in, fan out, and things like that. Fan in is everyone who's there that is importing me, or fan out is like I am importing class A, B, C, D. Interesting metrics, you can even stack them and see what kind of effects would happen. Very interesting and common combined metric would be source lines of code and a fan out, because by enabling those metrics, you can even see which nodes are maybe kind of problematic or hard to understand. A heat map is another very interesting technique in the form of visualization, and it does apply very good to software visualizations, to source code visualizations, because by enabling just a heat map, you can identify certain classes, certain files in a very, very quick way. And you can configure and define such metrics by yourself. So you by yourself define what is important for me. And just by switching and even adding those metrics to the heat map, I can very, very easily see, okay, which cluster, which part of the code is probably maybe even dangerous to me, maybe can suck up a lot of my effort. I can even prioritize refactorings on it. And I can use it for communication, even with non-technical people or with my other developers, to use such visualizations during plannings, to see what is the next step we want to refactor, what do we want to achieve. So that's fine for now. Then let's maybe dive deeper now with a Kotlin project. Again, we are creating a dependency graph. This looks less complex, to be honest, than the code base we've seen before, but it's fine. And we already see the algorithms are kicking in. So there are a lot of clusters that are really defined by colors and by their structure. This seems like a very modular and very, let's just say from a 2 steps back, it seems like a very clean architecture, which is good. And we can switch also between file and entities. Let's maybe apply some metrics here. A good start maybe to apply some metrics would be the fan-in metric to identify nodes that somehow are characteristics for their modules or for their clusters. Let's go for that. Jet news, interesting. So we know this module is called Jet news, has some maybe a kind of application, maybe a kind of example. Let's use a search for that. We search for Jet news and we identify basically the big blue cluster. There are some additional clusters, so probably some other modules that are dependent or that have some dependencies, but this seems pretty clear to me. Interesting. There are some subclusters which are not colored blue. Algorithm didn't pick that up. Why is that the case? The blue cluster you see right here was picked up because it is basically mainly about UI. So the classes, the entities, everything is like images, buttons, views, and stuff like that. And it does work out. So what are the other clusters that are directly connected? I mean, they are directly connected to this module, to this application. They are model classes. Still from Jet news, model, data, and end-to-end. Interesting thing, why the algorithm or both algorithms choose to color it in another way. That is an indication also for good modularity. Because you have a clear data layer, model layer, which is separated from the view layer. Makes sense. Again, we found out just this little insight in just a few seconds with very, very low cognitive effort at all. Let's make another step to this orange cluster, which also looks very promising. Let's have a closer look at that. So what is this orange cluster? Jet survey. Seems like another example, maybe another application, another module. Let's search for Jet survey, okay. Seems limited, maybe smaller than the first cluster, but it's still fine for us. What we maybe want to look now, because we basically don't know anything about this cluster. We see that it's kind of limited, but maybe there is something behind this. Let's activate a heat map. Seems it's pretty decent, to be honest. It's no danger, no dragons here. I would like to work on that code. Again, with just very, very small cognitive effort in just a few seconds, I can even zoom out, but I can identify maybe some potential classes or entities that could require more effort. Like maybe they are bigger, maybe they have more lines of code, maybe they have more complexity in a complexity metric, maybe they are more interconnected with other nodes. So still a cool technique. Everyone is a fan, of course, of unit tests. Let's try that. Let's search for tests. Yes, we found something. Another cluster, the red cluster. And interesting fact, a lot of code bases, you can find this kind of testing clusters somewhere if they have unit tests. There's a cool technique here which you can use to just directly see which parts of the codes are basically covered by unit tests. I mean, you can just mark this JUnit test base class and try to expand the connectivity graph just in 2 steps. We can directly see the interconnections of the other codebase modules that have some coverage of unit tests. Again, just 2 steps with basically no cognitive effort at all. The other insight I can draw from this, the other code is not unit tested. Again, base for argumentation, base for planning, base for kind of convincing people, hey, we need to write more tests. Maybe not here, but maybe on the other parts of the code. One last example I would like to show you is a small excursion into a Swift code base. So you see where this is going to. First Java, first Kotlin. I'm going to show you Swift. Kind of indication we're having a kind of language agnostic approach here. Wow. Some of you may know this like the big ball of mud. Everything is tightly coupled together. Everything is really dense. Let's just check with the heat map. Oh boy. I don't want to work with that code probably. So you see, there are a lot of possible classes, possible files that are either big, complicated, have a bigger complexity. Let's check the source lines of code metric. Ooh, what do we have here? Something is exploding right in our face. What might be this kind of file? Could you guess? Yeah, something emoji, something with emojis. Okay, basically really big white space complexity, big source lines of code, but it's basically just a list of a lot of emoji encoding, so it's not a problem for us. I would say it's even a false positive here. But it's okay, we can get the insights very quickly. Let's check another metric combination. There is another metric which I'm not quite sure originated from Adam Tornell. It's the white space complexity. So it is a similar metric to source lines of code. It does even behave very similar in a lot of scenarios. One benefit in white space complexity is that it really counts white spaces and is a bit more precise when it comes to only counting lines of code. It counts indentation and therefore is a bit more precise metric. So we've seen those things. Let's switch to the class view. This looks not so awful as the file-based graph, to be honest. It's not so dense anymore. It has not a kind of very, very aggressive coupling. Still, there are some nodes that got our attraction. But in the end, this is also a proof that like a file-based graph does not always have to look the same as an entity-based graph. But again, when turning on metrics, we can still find our lovely nodes. And yes, you've seen those nodes before. Again, the emoji things, now it's split into classes. One of them is even called just an emoji class. Interesting semantic keywords, by the way. Face, women, man, emoji. Seems to be fine, yeah. So a big thing, but we can put it away. We already identified this is probably nothing we should worry about. But there are other classes here that we can take a look at. So we already identified kind of maybe potentially problematic classes, complex classes. It even confirms with the heat map. And we already have the cluster mapping to this. So we basically can identify and know when talking about refactoring prioritizations or when talking about any kind of weird merges we are planning to do or any kind of structural changes. So we can, when we want to get to know a code base in a very fast way, we can activate a fan-in and fan-out metric. This is a very characteristic thing of putting those nodes in the front that really are characteristic for the code base. We have a conversation view controller. So let's try to find out what this code base is all about. Conversations. Next to it, messages, message action. Okay, we already found out it's about conversations, about messages. Let's use it in the search, maybe. Putting it conversation and message. Yep, seems that we covered at least some portions of the code. We found some classes, some entities, but it's still, I wouldn't say this is all. We can use something that is called a semantic search. It's based on a text mining trick, which is called TF-IDF. And it basically searches those keywords in a kind of, if there is a meaning in the document it searches. So it basically searches the entities for meaning. Is this a relevant keyword in this document, while at the same time it's not irrelevant in others? So we have covered quite a portion, I would say, with the semantic search included. Let's go in with a wild guess. Media. If there are conversations, if there are messages, there must be some media thing, right? We found something. Even a big cluster. Adding semantic search to it. We have even more. So what do we have? Conversations, messages, media. Trying to get a clear picture here. So what could we do? Let's make a wild guess and use all the three search terms we already found. Conversation, message, media, and let's add image to it because, we're just right at it. Adding the semantic search. And what you see right now, we have basically covered a very, very big amount of source code of this code base. So therefore, I would have no problem of just guessing this might be a kind of messenger app maybe that can deal with conversations. You have images, you can send anyone images and stuff like that. Very, very easy also. Just by using this explorative approach. So again, not a lot of cognitive effort, just using an interactive visualization to find this out. There are limits when using such visualizations. Yes, would be lying if I would try to convince you there aren't. If the graph gets too big, we lose overview and performance. That means, what do I mean with too big? Maybe something between 15, 20, 30,000 nodes. This would be probably too much. You would need a very, very strong computation to render it even on a display, but you won't have anything from that. So the visualization would make no sense anymore. What can we do about this? We create several graphs. We can look at a code base and then just plan to create maybe one graph for this subdirectory, one graph for another subdirectory, one graph for the other, and. So we can kind of solve this problem. Often metrics are limited. I'm pretty sure you know this. Please don't rely on just one single metric. Don't say something is really bad because it has a real big amount of code, or maybe kind of complexity metric says this is too bad. Maybe some kind of weird number, it's 7, it must be bad. That's not the case. Of course, there are limits. What can you do about this? Try to involve an expert. Metrics and a kind of combination of metrics should always be evaluated at least by experts. That means by us, developers. We should always take the time to even try to confirm it or even maybe rule it out as a false positive. We had the example with the emoji. Insights from metrics are basically heuristics. So we're dealing with uncertainty. We have a limited amount of metrics. Maybe our knowledge about the code base is also limited, so this results in heuristics. But it's okay for us until the amount of uncertainty is not too big. We can deal with that. One thing which could be a problem, we're just looking at one snapshot. So that means we're just looking at one point in time of the code base where the tool or the parser or the visualization was made exactly. So this is a kind of just one state. We don't know anything what happened before. We don't know anything if there were maybe reasons why this kind of structure is there. Were there reasons why this complexity is at this level? Were there maybe any reasons why this graph is so big, so small, and stuff like that? We don't know, to be honest. And that is a problem. I mean, developing software development is a process. We have no knowledge about everything that happened in the process. We're just looking at one particular moment in time. The question to the audience, can we do something about that? Can we solve this somehow? Anyone has an idea? Good, I like that. We might look at the history of things. So how do we do that? Great. Very good answer. So let's consider time travel. I'm pretty sure you know this movie. So the funny thing is, that was a very, very good answer. Git is basically our flux capacitor here. So we can use it to make this kind of time travel back in time. To maybe we can even set up the exact time we want to travel back with Git to see what was the state before. Was there any kind of problem? Was the complexity higher? Was it lower? How was the state of the interconnectivity inside the graph? I have some recommendations when we are here. Maybe you already read those books. Your Code is a Crime Scene or Software Design X-Rays by Adam Thornhill. Great books. They are quite like eye-openers to me, to be honest. Would recommend it to any software developer to have a look at that. The good thing is we are considering Git. So therefore, we can even consider classic software metrics on the dimension of time, like source lines of code, like complexity metrics. We could even think about considering graph-based metrics, fan-in, fan-out, import dependencies. They also can change, of course, on the dimension of time. Gets interesting here. And we can consider so-called temporal metrics, e.g. code churn. Pretty sure you've heard it before. Maybe you already know what it is. Or change coupling. There are a lot of more that Git can really give us from a metric kind of perspective, but let's just concentrate on those two. What is code churn? Always when I think about code churn, I have to think about meat grinding. You know, putting meat in a meat grinder and then you're grinding and something is coming out, maybe in a different shape, different kind of way. Always everything is get torn apart. For our vegetarians, let's maybe think about a leaky bucket. That may be a better practical example. So there is a leaky bucket, you power in some water will leak out of it. You power more, and then there's constantly a kind of flow. This is called churn. So that's maybe a good example. You add lines of code, you remove them, you add, remove, and there's churn. So basically, there are multiple definitions of code churn, but let's think about this leaky bucket. There is a lot of movement going on at this place. Another thing, change coupling. What is that? So I'm pretty sure you all are very familiar with coupling and cohesion. Classic coupling and cohesion. So you try to always to detect or to prevent a strong coupling, and you always try to facilitate a high cohesion, which leads you to modularity, which is a good thing. The question would be, can we use Git to maybe also have a kind of change metric? Yes, we can. So just think about it. And this is not my idea. This is also from the books of Adam Thornhill. Change coupling is defined like this. are there files that change in Git commits together? And now think about it. Yes, of course they are. It can be understandable because maybe those files, they belong into the same cluster. They maybe import similar nodes from the same cluster, and that is fine. But sometimes you can detect some even weird anomalies if looking at change coupling, because sometimes classes changes which are maybe not directly connected in the same cluster. They may be even really far away. They maybe even have nothing really to do with the kind of module that you are maybe working or that the commit is about. I mean, there can be some problems because we all know we like to have big merge commits. So this is a problem for that. But still, there can be nice indications. Change coupling is a really exciting topic which can get you a lot of insights. I will show you an example. And again, we're going to a Java example, but this time we activated our flux capacitor, Git, and let's have a look at that. Obviously, you can see directly you have more options on the right side. That's good. Still looking at a kind of decent code base. I will not spoil you and tell you what this is. It's a famous open source project. And we have more metrics available. So we can look at code churn. We can look at the number of authors. We can even consider those classical code metrics that I mentioned. Source lines of code, white space complexity, and. So there are basically no limits. And we can interactively use this kind of approach to explore the code base and, in addition, what happened with the code base, to explore the past. What were the changes? We can set up even a time range or maybe just one particular day, so we can time travel back and have a look at it. How is maybe our code churn at this specific range? It's not so big. Seems like a good thing. We can even confirm this with the heat map visualization. Different kind of heat maps, a churn heat map, hotspot heat map, which also can take like classical metrics and temporal metrics both into account. And if we change back the time, then we see, yes, the heat maps, of course, will change. So we can play around with this, which is quite a cool thing. Because just from those things, you can already get more insights. You can, basically learn the history of the code base in an explorative and, let's just say, easy, understandable approach, which takes low effort. Change coupling, I was telling you about this. This is a chord diagram that basically represents which files are changing with which other files in the same commits. It is a good thing when you see the blue color, it originates from the blue cluster, so that is a normal thing. Files that are part of the same cluster, they tend to change together. Sometimes you can spot some anomalies, like the purple cluster. In this case, it's a kind of configuration versioning file, which is also okay. But there are also some things that can be weird, that maybe need to have a closer look, especially when you have some files with maybe just limited colors, and they are changing maybe on a daily basis, step by step, every time. Interesting instrument. One other thing we have, since we are using Git, we have contributors, we have authors. That's a good thing. Anyone from VMware here? That's good. No, not a bad thing. Just searching for contributors for the part, and what I'm seeing right now, that for the certain amount of time where we traveled back and got all the information from Git, it seems to me that there are a lot of contributors from VMware, especially in this code base. This is quite interesting for us. Why? Because we can have a look or maybe think about ownership, think about, maybe this guy or those two guys, they are not even there in a company. What can we do? Distributing ownership, thinking about main contributors even. So kind of a lot of new insights that we can think about, that we can plan in, that we can consider in this approach. So it's time for a summary. Pros and cons, of course, there are pros and there are cons. One good thing is the change of perspective. You can see previously overlooked details and relationships. We've been having a look together at the examples that I've shown you. Sometimes when we developers, we're developing, we're using our IDE, we get lost in details. Such visualizations can help us, can help anyone to take 1 or 2 steps back to see the big picture. This basically, it's what it's all about. The technical understanding and decisions, we can facilitate this with just little cognitive effort. I mean, we've seen it as in the demos. It was so easy to find out interesting details about code bases in a kind of explorative way, in an easy way with very, very less or nearly none cognitive effort at all. Developers, we all can do this, but even a lot of non-technical people can do this, or even maybe at least can understand and follow the argumentation behind this. It's a kind of language agnostic approach. I've spoiled that already. So we've seen Java graphs, we've seen Kotlin graphs, we've seen Swift code bases. You can extend this to a lot of more languages, to Groovy, to Python, to JavaScript, to TypeScript, doesn't matter. Works with a lot of languages that kind of provides us the relationships of dependencies. Visualizations, again, I've told you in the story from the beginning, can be a good way of providing, can be a good foundation of starting a good discussion, of providing the ability so that every stakeholder can communicate with you on the same basis. Time to use more visualizations, I would say. A con, of course, if such graphs get too big, I already told you, you lose benefits. You lose benefits in the way of performance, you lose benefits of the nature of the visualization itself, because if it's too big, if it's too complex, it's getting useless. And one thing, sometimes our flux capacitor, Git, in this case, can be slow. I mean, Git mining is it's not a new topic, basically. As far as I know, there are no really, really very fast approaches where you can mine Git data. At least I haven't found an algorithm that I could use. But who knows? Summary and takeaway. Consider visualizations for a change of perspective and less cognitive effort. If you don't already know them, take your time, read Adam's books. It's more worth the time, I can promise you that. And yes, you can use Git as a flux capacitor here. And by the way, while using such interactive visualizations and trying out those approaches, basically you can learn a lot about software architecture. Be open-minded, try out interesting ideas, implement them, release them, make them open source, let other people contribute, share your ideas. Some recommendations. Again, your code is a crime scene, software design X-rays. There are no affiliate links, so don't worry. Another thing that I would highly recommend to anyone who would like to get into the topic of understanding legacy code is the website understandlegacycode.com by Nicolas Carlo. Here's a QR code if you want to scan it. It's a great resource of information about how to, what are approaches to work yourself into the code, what are maybe good techniques to prioritize refactorings, what is a good refactoring, what is maybe considered not a clever refactoring. A lot of articles from Nicolas Carlo, highly recommended to anyone who wants to go deeper in this topic. Adam Tornhill also has a very, very nice tool. I wouldn't even call it a tool, it's a kind of software platform. It's called CodeSteam, also very, very good. It's kind of similar to this amateur tool I've shown you from me, but this is kind of professional tool. You can use it for free for any private project, so that's a very cool thing. And if you want to use it for a commercial product, you have to buy a commercial license. Still very cool to try it out. You can find even more details with change coupling and Git metrics in this tool. Great. And because this is such a great conference, just today in the morning we have a special Devoxx Poland release of this tool I've shown you in the demos. Just clone it, you can install it via pip. It's a Python tool. Try it out. It is probably very unstable right now because I've added a lot of features with the temporal stuff. Of course, you can file feedbacks and issues. Please don't overrun me with issues on just one day. Give me a chance to fix it. But I'd love to if you would like to try it out and give me any kind of feedback, or maybe even contribute. Maybe have some own ideas. Thanks for hanging in. Enjoy the rest of the great conference, and I'd love to get in contact with you via Twitter, Mastodon, LinkedIn. Thanks.